Welcome back. Today we're going to talk about model evaluation with cross-validation. So last time we talked about a best practice in evaluating machine learning models and we called it the holdout method. And the idea behind the holdout method was that we set aside a portion of our data for testing purposes and we don't touch that part of data for training. So imagine I have a data set and I have 100 rows of data in it, 100 training examples in it. And so what I'm going to do, I'm going to set aside maybe 20% of that data for testing. And I'm going to use the other 80% for training my machine learning model. So 80-20 or 85 15 or 90-10 are pretty common numbers for splitting your training data set into a train set and a test set. So now if you think about that 20% that I set aside, there was nothing special about it. The only thing special about that 20% was that it was not used in the training process, and it could be any 20% of the data selected randomly. And so we're going to extend that idea and talk about another best practice in model evaluation, which is called cross-validation. So if we look at the 80% of the data that we are left with for training, one thing I can do is I can measure my model performance on the training data using this 80% of the data. So, and that's going to give me a number. It could be the typical metrics that we use: accuracy, precision, recall, F1. But I'm getting one single number that kind of represents the performance of my model on the training data set. And I can compare that to my performance, my model performance on the test data set. And depending on what happens, if the performance metrics on testing data set are better or worse compared to the training data set, I can diagnose the problem and kind of see if my model is underfitting or overfitting, and then go back and make changes to my model to improve my model and then redo the testing. But one thing that I'm doing here is that I'm relying on a single number to measure the accuracy of my model or any metric for that matter on my training data set. So what I'm gonna do, I'm gonna take these 80% of my data, and what I'm gonna do, I'm gonna split this into folds or parts. So let's say I'm gonna split this into 4 parts. And so this is gonna be fold 1, fold 2, fold 3, and fold 4. So I took my data and I split it into 4 different parts. So if I had 80 rows, 80 training rows in my training data set, now I have 4 folds, and each fold is going to have 20 instances or examples or training rows. So now what I can do is, just like what I did with holdout validation, I can use any 3 of these 4 folds to train a model and then test it on the last fold. So in this case, I can use fold 1, 2, and 3, and I'm left with fold 4. So I'm going to use it for testing. And if I do the testing, I can basically produce my performance metric. Let's say I'm measuring accuracy, but it could be any of the 4 metrics that we've talked about: accuracy, precision, recall, F1. So from this, I'm gonna compute my first accuracy number. Then what I can do is I'm gonna say there was nothing special about fold 4. Why not use fold 3 for testing? And so if I set aside fold 3 for testing, the 20 rows in fold 3 for testing, now, again, I'm left with 60 rows to train. So, and that's gonna be folds 1, 2, and 4. And again, I can compute another accuracy number. I'm gonna call this ACC2. This is my second measurement of the accuracy of the system. And so I can repeat this process. If I have 4 folds, I can do this 4 times. So next time, maybe I can basically use fold 1 for testing, and that's going to give me 2, 3, 4, 4 for training. And again, I'm going to compute my accuracy number. And finally, I can use fold 2, the 20 rows in fold 2 for testing, which is going to leave me with 1, 3, and 4. And again, I'm going to compute my accuracy measure or whatever measure I'm interested in. And so as a result of this process, as you can see, I'm generating 4 different values. So if I'm doing a 4-fold cross-validation, I will generate 4 numbers instead of 1 single number. And so one thing I can do, now I can compute the average of these 4 numbers and report that as my model performance on training data. And I can also compute the standard deviation of these numbers to see how far apart these numbers are when I'm testing my model on a different fold. And a combination of the average accuracy on these 4 numbers and the standard deviation can give us a better sense of how well my model is performing. So basically, I'm going to say my model is performing on average by this much plus minus the standard deviation. So that should give me a range of numbers. And from a statistical point of view, because I used 4 different numbers, my estimation of the accuracy of the model is much more stable, because now instead of just relying on 1 measurement, I did 4 measurements. Typical numbers for cross-validation are 5, so people usually will talk about a 5-fold cross-validation. Sometimes it's called CV, standing for cross-validation, or 10-fold cross-validation is very common. One thing you have to pay attention to is the reason we are doing the cross-validation is because we want to get a more stable estimation of the accuracy of the model on our data set. And typically, if you have a large data set with lots of training rows in it, you can do 10-fold cross-validation or 5-fold cross-validation. But if you're working with a really small data set, like in my examples, it was kind of unrealistic. I said imagine I'm using 100 rows and I set 20% of it, which leaves me with 80% for training. So I have 80 rows, and 80 rows is really not that much. When I'm doing my 4-fold cross-validation, I only have 20 examples in each fold, and so that's not a large enough number to be reliable in terms of computing performance measures like accuracy or precision or recall or F1. And so if my data set is small, like in my example, I only had 80 rows or 100 rows, I wouldn't do a 10-fold cross-validation or even a 5-fold cross-validation, because what happens is that when you measure the performance of your model on your test fold, when all you have is 10 rows or 20 rows in that test fold, your numbers are not gonna stable. You just don't want to basically look at 10-20 rows and whatever accuracy you compute, kind of take it as the accuracy of your model. And so with a smaller data set, you have to decrease the number of folds. So maybe you would do a 3-fold cross-validation. But if you have thousands of rows, then you are perfectly fine to do a 10-fold cross-validation. So it really depends on the size of your data. But this is going to give you a second very good approach to evaluate the performance of your model. So if you combine the first method that you learned, which was the hold-out validation method, and if you combine it with cross-validation, you pretty much have all the tools in your disposal to evaluate your models. So now let's go back to our code and see how we can implement this concept of cross-validation. So if you remember, in previous sessions we built a classification pipeline, and we measured the performance of that model using the standard metrics, and we set aside a portion of our data for testing, and that was holdout testing. And so today what we want to do is to implement this idea of cross-validation. And again, we are using scikit-learn as our machine learning library, and scikit-learn comes equipped with utility functions that you can use to implement all these ideas. So the first thing I'm gonna do is I'll need to import the function that does the cross-validation, and it's going to be under the model selection module in scikit-learn. Previously you've seen train test split from this module. Now today we're going to use something called cross-validation or cross-val score. So this is going to compute the cross-validation score for us. And both of these things are under model selection, and the reason behind it is these are the kind of things that you do to properly evaluate a model or different models, because you want to pick the one model that performs best for your intended business use case or for your data set. And so kind of splitting your data into train and test, or using cross-validation as an approach to evaluating your model. So all of these are part of the model selection process, and that's why in scikit-learn you have this module called model selection. So when I'm doing the cross-validation, this is gonna, as you learn, this is gonna generate different numbers. If I'm doing a 10-fold cross-validation, I'm gonna get 10 accuracy numbers, or 10 F1 numbers. And so we need to average these numbers and compute the standard deviation to kind of summarize our evaluation results. And so to do basic things like averaging or computing standard deviation, I'm gonna need to use NumPy. So I'm gonna import NumPy for basic functions like average and standard deviation. So I had a typo in the module name, which I corrected, so we're all good now. What I want to do is I'm gonna have to, so basically I'm gonna define a variable scores. This is where I'm gonna store the different numbers that I get from my measurements. And so I'm gonna call this function that I just defined cross-validation score, and the first parameter is the model that we're estimating. We already have a pipeline, so that pipeline is our model or our estimator, and we call this the classification pipeline. So this is the pipeline that we've been creating over the past few sessions. So this is the model. The first parameter is the model that I'm trying to evaluate. Next parameter is gonna be my training data set, and we called it xtrain. If you remember, when we did the train test split, the training portion of the data was called xtrain, and we said we typically use the variable x as the training data and y as the labels. And of course, we're gonna need the correct labels, or the ground truth labels. Anytime you measure accuracy or any metric, you need to have the ground truth labels. The final parameter is going to be our CV. So are we doing a 4-fold or 5-fold or 10-fold cross-validation? And here I'm just going to go with, I have enough data to do a 10-fold cross-validation. Let me print these numbers to actually see what we get. What are the 10 accuracy numbers that we got? So we can say 10-fold CV result, and this is what we're gonna print, scores. And as you can see, what I'm getting is 10 different numbers. And as you can see, I have 91%, 97%, 97%, 91%, 93%. So as you can see, because every time the data that's being used to train and test, I'm getting a different number. So instead of just saying my accuracy is 91% or my accuracy is 93%, we know is going to be dependent on which set of rows were used to train and test the model. We're going to average all these numbers, and that's what we're going to report. So what I'm going to do, I'm going to average these numbers, and that's what I'm going to report. So I'm going to say cross-validated accuracy or average cross-validated accuracy, and for this I can say numpy.mean, and I can pass these 10 numbers and compute the mean, and I can say plus minus numpy.std, which is going to compute the standard deviation. So again, we need to pass scores as the input to the standard deviation function. And so if I run this, what you see is that instead of reporting 10 different numbers, now what I get is my model is performing on average 95%, but we know there is going to be some variation, and the expectation should be that I might have 0.02 standard deviation. So basically, I should really expect to get a performance kind of in the range 0.93 to 0.97 from this model. So it seems like we have a reasonable model because our average training accuracy when we measured using cross-validation is around 95% accuracy on training data. And if we look at the testing that we did last time on our holdout data, this was data that was never used as part of the training. And here we get 94%. So 95% plus minus some variation, and 94% here for our holdout. So the numbers are close together, and so this is a reasonable model. It's not underfitting or overfitting. So far we've spent some time talking about the steps before and after building a model. We talked about pre-processing before building a model, and we spent the last few sessions talking about model evaluation. Now what we're gonna do in our next video is to focus on model building and kind of learn about best practices to train models. I hope to see you in the next video.